finished off chapter 15, and we've currently been focusing on linear momentum. But remember that we also have conservation of angular momentum, so we're going to have to deal with that rotational motion. So I want you to think about billiard ball problems where we're going to have rolling. Think of cans rolling down an incline. Think of gyroscopic motion. We're going to have to incorporate that angular momentum. And just within just with what we had with statics, we want to move from that purely physics definition to an engineering one. So we're going to start to see, remember, instead of having torque, we ended up having moments, and now we're going to have to bring in that moment. I want to point out a couple of videos that you might want to go back and look at that actually show you some real world type applications of angular momentum and kind of looks at those particular aspects. So those are really, really good aspects there. And just as I've done before, I want to acknowledge that I'm going to be using some of the Hibbler slides. And when it's a Hibbler kind of an item, it's going to be in the Times New Roman font. So just kind of give you an idea of which I am using, and those are being used with permission. So we're going to look at that angular momentum, and just like what we had back in statics, where I moved from torque being that physics definition to a moment being that engineering definition, we're going to do the same thing here. So angular momentum about a point O is defined as the moment of the particle's linear momentum about the origin. Remember also, I'm going to have a right-hand rule that's going to come into play because I'm going to have to deal with that cross product. So just like what we saw in statics, I'm going to use that angular momentum, and we're going to use the letter H here to represent that angular momentum, and we're going to have to use that cross product that we're going to have to come in with, so that's going to give us our right-hand rule, but the magnitude is going to be the mass times the velocity times the distance. And if you think back in Engineering Physics 1, remember that we had angular momentum being mass times the velocity times the radius. So we're dealing with that distance, we're dealing with that arm that's out there, and remember that this is going to have some strange units. It's going to be kilograms meters squared per second or slug feet squared per second. So we're going to bring in that moment aspect, we're going to bring in that angular momentum aspect of the problem. So just like what we saw in statics, just like what we saw back in engineering physics, that we're going to relate that angular momentum back to something slightly different than what we had in linear. Remember that we had the moment of inertia times our angular acceleration was going to give me my sum of my torques. And so here we're going to get that same thing that's going to happen with our linear momentum. We end up with, that's our linear momentum with the L, and we've got our mass times acceleration. But our moments is going to be our cross product, and we're going to get our angular momentum. I do encourage you to go back and look at your textbook. It follows through, and it does a lot of good diagrams here, but we're going to get those cross products. So I want to kind of also remind us that our velocity, the first derivative velocity with respect to time is going to give us our acceleration. And now when we look at this with our cross product, we're going to get this same type thing here, and we can look at it in terms of this aspect. Please go back and look at that derivation in the book because it's really, really going to help you out. So that's where we get. So now if we have a system of particles, or we're expanding to that physical dimension, I don't just have one particle, we're going to use the same equation because I'm going to take the sum of all of those. I'm going to get the sum of all of those parts, and we're going to start thinking about, remember, I have moments of inertia. Remember that I'm going to, a hoop is going to behave differently than a baton with two weights at the end. And those are going to behave differently than a solid cylinder or a cylinder with a hole in it. We're going to have to look at that sum of those different particles. So the force is acting on the ith particle of the system. I've got internals, and we can do the moments can be written as the sums of our angular momentum that we have to encounter. So the second term's here, so we can do those sums, and just like what we have applied in our statics, except now we do have motion, and we can't just set all these things equal to 0, because 0 was our equilibrium representation. Now we have to account for things that are actually in motion and are moving. So we have that particular stuff. So here's my angular momentum, and I've got, considering that we have a relationship between moment and time, you know, I've got my first derivative with respect to time. We can look at it and give ourselves a similar impulse equation, just like what I've had before. Just like what I saw with my linear momentum, now I've got a similar equation that I have with my angular momentum. And this is considered our principle of angular impulse and momentum. And in the case of two-dimensional motion, it can be applied to scalar components in dealing with our z-axis. So we know we can actually utilize it. So we're taking an expansion here. The sum of the angular impulses acting on the particle during the time is conserved. We have our conservation equations, and this condition allows a particle subject only to a central force. We get the angular impulse of the force about 0 is always 0, or about our origin is always 0, and the particle is also conserved. So we're going to extend what we saw earlier in the chapter to now bring in this angular component, but the problems are going to work very similarly. And please go look at those example problems that I'm going to get posted, and that's really going to help you out.